So anybody up for that? Come to my house. It's all about the scary beasts. And then he wonders why he has nightmares. So, what's going on? How's the world out there? You know, I go on these walks because I've been rehabbing my knee. It's been 50 days in a row. I've gone on walks about 4 miles a day, sometimes 5. And yeah, with the weather getting nicer, I see some other people have, you know, shed the winter coat. That's good. It's a beautiful thing. So anyway, that's my little tentacle out to the outside world. It's been a year. Can you believe it? Wow. And we'll see what happens in the fall. Nobody knows. The official word is that we don't know yet. In case you were wondering, faculty talk about it all the time. We really don't know what's going to happen in the fall. I'm hoping that we'll get things under control. Maybe, and this is just me thinking, this is not an official statement from the college, but I'm thinking that they might require either frequent negative tests or vaccination. But I don't know that. But we'll see. But then it would be nice to be on campus. You guys got a rough year here, being off campus. Or for some people it's been rough. Some people maybe not so rough, but definitely different. So hope you were able to carve yourself a nice niche, nice little life to live in for a year. But just hang on for a few more months. Let's see how the summer goes and all that. So yeah, Rosette groups. We're going to do what I'm calling Rosette Arithmetic today. And basically what that means is these objects that we can now classify as a C2 or D3 or C5, we're going to do some math with those. And you might be wondering, wait a minute, how can you possibly calculate with symmetries? What kind of calculation could we possibly do? What kind of symmetry crunching is even possible? Yeah, that's a good question. And I'm going to answer that today. It is possible. And it's a new way of looking at, I'm not going to call it number crunching, but crunching things. Like Moxel likes to smash things. It's like anytime I get a sequence of elements, I want to smash it together and make it the tiniest thing that I can. He kind of works like in one of those those car crushing lots. What do they call those? The demolition. The ones that make the cars into little cubes.
Yeah, like the junkyard thingies. I know what you're talking about. I don't know what they call them.
Yeah, you see it in the movies. They'll take a bunch of cars and just make them into these like little, the smallest pot. They take all the air out and they squeeze them, all the garbage into the tiniest space possible. Well, that's kind of what we're going to be doing today. I bet you didn't think that I could have a segue out of that, but that is what we're going to be doing today. We're going to take sequences of things and make them into the smallest thing that we can. In other words, we're going to be simplifying a sequence of symmetries. Wow. I mean, what does that even mean? Let's get started. Let's get started. So I'm going to share a whiteboard with you, and basically what I'm going to do now is, remember at the end of last time I warned you against reading section 5.2, the Rosette groups point symmetry section that starts on page 138. I said basically don't
Yes, I
read
remember
it.
that.
Yeah, it's unusual advice, but I still stand by it. It is something that I feel like I need to kind of break it down to you into more palatable chunks. And that is what we're going to do today. So, but just so you know, you will be responsible for this this kind of math after today. And so this is from the book, starting page 138 and onward. And I'm going to call it AKA, also known as set arithmetic. Now, if you Google that, you're probably not going to get anything. I just made that up. But that's kind of what I feel like we're doing when we're doing this. We're taking these different symmetries, whether they're rotations or reflections, we're going to take them and combine these things and then simplify them. That's the gist of it. So if you're wondering, what is he even talking about, combining symmetries or whatever, well, let me just back up a little bit and simplify the picture for you right now. As an example of what we're going to be doing, I'm going to be talking about one specific group, and that's the D3. D for dihedral, you remember that? D for dihedral, and 3 for the number of rotational positions that an element has. So here is the easiest, the clearest, the simplest example of a D3 Rosette group. So our example is D3. Now, all of this stuff that I'm going to be talking about is going to apply for every other Rosette group, like D2 or D4 or C3, C5, C50, D100. All of these things exist, and I think once you get the hang of the D3, you'll be able to work the rest of them. D3 is just the right amount of complexity for demonstration. It's got a little bit of everything. It's not too simple, but it's not too complex either. So D3 is a great example. It was not chosen by me. This is from the book. Starting from page 138, you have the example of the equilateral triangle, how it can be used to illustrate what I call the R's and the F's. So I'm going to call this first triangle 1. And here's how it's oriented. I'm going to label the, although an equilateral triangle, of course, it's, all the vertex angles are the same, all the edge lengths are the same. So in some sense, all of these vertices are exactly identical. However, there are still ways that we can manipulate the triangle. And if here I made this little triangle with A over here in the lower left, and wait, is it lower left to you? Anyway, in my picture here in the screen, it's the lower left. C at the top. So A, B, C. If you go counterclockwise, you see A, B, C. C at the top. So I'm going to call that my original position. And for simplicity's sake, I'm going to call that position. Every position is going to have a name. And I'm going to call that position 1. So basically what we're going to be doing in the next 15 minutes maybe, is finding out all the different orientations of this triangle. So if this was the original orientation, then how about some other positions that look the same from far away, but then when we look at the vertices, we see, oh yeah, A is not there anymore. A is, in a different place. So this study of symmetry, this Rosette arithmetic, looks at an object, and we look at how many different ways, first of all, we can orient the thing and it still looks the same. So for instance, I can rotate the triangle so that I still have a flat side on the bottom. But if I rotate it, and let's say we're going to rotate it counterclockwise. So A on the here, in the lower left will now be in the lower right. B will go on the top, and C will be in the lower left. So I'm going to rotate this thing. So rotate counterclockwise, CCW means counterclockwise, by 120 degrees, right? And what I end up with is, let's see, so A would go to the bottom left, B would go on the top, and C would go on the bottom left. A is on the bottom right, C is on the bottom left. So notice that from far away, if you didn't know how the labels or how the vertices were labeled, then you wouldn't know any difference. You wouldn't see any difference, right? And we just rotated this thing 120 degrees, but because we're paying attention to how the vertices are labeled, I can differentiate between the first one and this one. And I'm going to give this position a name. If the first one was called 1, and this is now rotated, so I'm going to call this R for rotated. Okay? So the first one, the original position is called 1, and then I rotate it. I'm going to show you in the picture. You guys can see me in the small screen.
Yeah.
Yeah. So on the bottom left, I had A, and then B on the bottom right, and then C on the top. If I rotate it once, notice what happens. A on the bottom right, B on the top, C on the bottom left. Okay, so this is called R. Now, what if I rotate it again? That's certainly an option that I have. Start it here, rotate once. If I rotate it again, notice that A goes on top, B goes in the bottom left, and C goes on the bottom right. So that is, again, a different orientation. We have A on top, B on the bottom left, C like that. Now, rotating once was called R. Rotating twice, I'm going to call I'm kind of thinking like in terms of multiplication. So R times R, R times R. So RR, or what ends up being a handy way of writing it is R squared. I call it R squared. So let me go back. I know I'm like going on about this rotating thing for a while now, but this really is a new way of looking at things you can do math with, right? You didn't even know you could do math with a triangle. Like, what kind of math is there to do other than like proving stuff? We're not proving anything. We're just looking at how a triangle could be oriented. So it could be oriented like this with A in the bottom left. It could be oriented like this, A in the bottom right. It could be oriented like this, A at the top. Now, what if I rotate it again? What happens?
It's back at the starting position. It's back at 1.
That's right. It's back in the starting position, back at 1. Wait, that sounds like somebody's album. Back at 1. Oh my God. Don't tell me. Do you know whose album that is? It's called Back at 1. Sorry, I haven't thought of that. It's everybody's favorite, R. Kelly. Yeah. Let's try not to bring R. Kelly into this. It's got nothing to do with rotating triangles. All right, so I know R. Kelly gets a bad rap, and for a reason, by the way, just for the record. So here, 1, R squared, and R cubed is back at 1, right? So I wrote down an identity that I can use. R cubed equals 1. So each time I rotate this thing counterclockwise, I'm calling it an R. Like, basically, you're multiplying it by an R. So if I'm at R squared and I want to multiply one more time, I would think of it like, R squared, and if I rotate it again, you think of it like multiplying, like I'm tossing in another rotation in there, and so that would then be, R 2 plus 1, which is R squared, which is, if I can fit it in, 1. So if you were to combine something called R squared with something called R, then we'd end up simplifying it to 1. Now, what are these things anyway? Well, like, what's an R squared? Well, we call them elements. And we call them elements of a group. A group, and just how we're going to define it is a set of all possible orientations of an object in D3, let's say. But this works for any group. So if I had a D4 object, by the way, can you give me an example of a D4 object that would be easy to manipulate like this? A D4
A square?
object. Square
Yeah.
would be perfect. Yeah. Nicolette, Matthias, yeah, you got it. So square would have one more rotation option, right? The square, and then once rotated, twice rotated, 3 times rotated, and then 4th time would actually get you back to the original. So this 3 up here, if everybody could look at this r cubed equals 1 statement, this 3 comes directly from D3. So the number that you have in the name or the classification of the object is the exponent that will get you back to 1. Okay. Now, this is not it, actually. There's more that we could do. Check this out. If I'm here in the original position, I have another little maneuver up my sleeve. I can do more than just rotate. What can I do with the D3?
Could you flip it?
Yep, that's right. That's exactly right. So I can flip it. And here's what it looks like. That was exciting, right? So I started here, and it's a quick operation. And let me draw some more triangles here. So here is my triangle that will be flipped. If I flip it, and I'm going to flip it across the vertical, axis. I'll just say vertical line down the middle, right? So I'm going to flip it across the vertical line that goes through the top, like just down the middle, right? And so what happens? What happens to the letters? C will actually stay exactly where it is.
Yeah, but B and A would flip.
That's exactly right. Perfect. Thank you, Fiona. So A and B will reverse. So top will stay in place, and the corners, the A and B, will reverse positions. And we're going to call that, see, it's a reflection, right? But I can't call it R for reflection, so that's why I'm using the word flip. And that's why I'm going to use the letter F. So now I already have 4 different orientations. I bet at one point in your life, maybe up until this one point, you've thought that there's really only one way you can look at a triangle, an equilateral triangle. But I've already shown you 3 different orientations of this thing. It's got 3 rotational positions, and then we're going to have these flip elements. So in fact, I can do rotation first and then flip, and that's going to give me a different configuration of the vertices. Oh no, I did a freehand triangle. Doesn't look good. B is going to stay on top, and A and C are going to flip. So that's going to give me, can anyone guess what I'm going to call this thing?
FR
I did the rotation first.
or
So
RF.
I'm going to call it RF. But yeah, those are the 2 letters that are in the name. So R first, then F. So what that would look like with my little green triangle here is rotation first. So I'm going to just rotate it once like this, and then flip it. And notice how I have my vertices. I have A on the bottom left, C on the bottom right, and B at top. Okay. Now, I'm sure you can guess now that we're going to have a third flip element, an overall sixth possible orientation of the vertices of an equilateral triangle right here. And let's see what happens to the vertices. A is going to stay on top, untouched, and C and B are going to flip out. I hope no one's flipping out in the crowd. It's really not that complicated, but it is different. I mean, I understand. You've never seen this before, so I'm going to try to take it slow. But this would then be called R squared F. R squared F. And these are the 6 elements of D3. So I'm going to write here, D3 has 6 elements. And sometimes you see this notation, D3, and it's got like a bracket. We have a 1, we have an R, we have an R squared, we have an F, we have an RF, and then we have an R squared F. Like that. Now let me just type in the little squares. This is not exactly the most user-friendly program for presentations, but here we go. So D3 could be written in that set notation, what's called a set notation with those brackets, those curly brackets. It's got 6 elements. 1, R, R squared. Those are my, what I would call rotational elements. That's the top row. So that's 1, R, R squared. So I didn't use any flips, right? I used rotations only. And then I have my 3 flip elements, F, RF, R squared F. And for those, there's an F in all of them. So either we flip 0 times, we flip once, we flip twice. Oh, I'm sorry. Either we rotate once and then flip. Let me back up again. Either we rotate 0 times and flip, or we rotate once and flip, or we rotate twice and flip. Rotating 3 times and flipping would actually just be a flip because you have that R cubed equals 1 identity. Now, let me ask you, can you think of an identity with the flipping? What can you tell me about flipping that I could write down as kind of, how should I say, an absolute fact? And as a hint, you can think back to that true mirror. What did I say about that true mirror? You think that was just a unrelated story? No, it's not. Remember the true mirror that I used to look at myself in at Ludlow Street?
Yeah, in the bathroom of the bar.
That's right. That's right. What I remember of it was that there were actually 2 mirrors in there. So what I was seeing was a double reflection. Because I had to study it. I Googled it. I mean, back then, late 90s, so mid 90s, there was no Google. But as soon as I could, I found out what the deal was. There was 2 mirrors angled just right. And so basically what I was seeing, what the customer would be seeing, is a double reflection of themselves. And it looked exactly like me. It was not a mirror image. Okay, so that's my hint. So what kind of identity do you think I could write? Just like I wrote an identity with the rotations. I know this is a lot to take, and this is a heavy lecture because it's well, Moxel set the tone. He's a heavy duty guy. He's nobody to mess with, and so Moxel here, yeah, he's probably the one to blame. This is a lot to take in.
To be honest, Professor, like I understand what you're like explaining here. I just like
Yeah.
I don't know what you're asking of us right now.
Okay, see how I circled or I rectangled r cubed equals 1?
Oh, okay.
So I
What do
want
you-
something that equals 1. I want an identity using the f.
Oh, okay. All right.
What is an identity I could write as kind of absolute truth that involves the letter f?
Did you say r squared f squared or r cubed f? Actually, I don't know. Wait, no, r
Yeah.
cubed f squared. Would that be right? Because then you're doing
Well,
two.
yes, but that's actually like two separate identities. So r cubed we already wrote. I think what you're thinking is, or maybe you're thinking too much. I'm just thinking f squared.
Oh, yeah, I was thinking too much.
Yeah. So, but you were on the right track. So here's what it is. Okay. So here's original. Here's 1 time flipped, and here's another time flipped. If I flip it again, I go back to 1. I go back to the original, right? This is, I totally get it. You see all these letters and exponents and oh my gosh, never seen it before. You start thinking, oh, okay, I better step up my math game. I mean, well, that may be true, but it's really not that complicated. Once you kind of get what we're trying to do here, we're manipulating these different elements, different orientations of an equilateral triangle. So yeah, it is a bit to take in, but it's actually not that complicated once you kind of put yourself in that mindset. So f squared is 1. What that means is if you reflect something twice, you're looking at the original. And that was the idea of the two mirror. You're not just looking at one mirror. It's actually a sequence of 2 mirrors, very cleverly put in there, and that's why the box was a little bit thicker than a normal mirror, because there's like 2 mirrors at angles. But as far as our triangle example, it's actually probably easier to see that way. Are you guys seeing these letters? I've got A in here, B in here, and C at the top.
Not
If I
really.
flip it,
It's 'cause it's
okay,
small,
man,
but, like,
I
it just
should have
goes
written in
small.
black. Yeah. I wonder if I have a black marker here.
You can kind of see them. I mean, you're just like a really small corner of my screen. I don't know if that's the same for everybody else, but that's the only reason I can't see them.
Oh, I see. Okay, yeah. So it's not maybe the contrast so much as
Yeah,
just the
it's just since
size
you're
of
screen
size
and
of it.
smaller.
Okay.
Yeah, there you go.
Well, it's not even. Yeah. Okay. I got you. So, A here, B here, and C here. That's a good point, Taylor. You can I guess pin me. You can put me in the main screen for yourself if you need to see me, or if you need to see this triangle better. But so I've got A, B, and C here, and if I flip this thing, they go into a different orientation. So now C stays on top, but the A and B reverse. They change places. Now, if you do it again, all that happens is that A and B go back, right? So it's like this. If I do a double flip, I go back to the original, right? Yeah, thank you, Taylor, for that. That's a good piece of advice. So A and B flip, they switch places, but if I flip it again, they switch back. That's all it is, really. So f squared equals 1, looks like some, high-flying identity or some math fact. But all I'm really saying is if you reflect something twice, you go back to the original. Okay, so this is the set of elements and the two main identities for D3. We've got r cubed is 1, f squared is 1. So for instance, if you had a situation where you had a sequence of elements like, let's say, r squared times r times f times r cubed times f, that's a cube, by the way. What would that simplify out to? Okay, r squared, that's a 2. R squared and r is just r cubed. So if you rotate twice and then one more, it just cancels out. And then you have f, and notice r cubed here, that's nothing. It's, if you spin around your axis once, you might feel a little dizzy, but you just you look the same to anybody. Like if you're walking and you spin around once, and you just keep walking, then you're still, it's like nothing happened. People might think you're a little funny for doing a spin, but you're facing the same way, you're oriented the same way. They couldn't tell the difference. They might have seen you spinning, but anyway, you can kind of just take that out. R cubed is like nothing at all. Nothing happened. And then you have f and f left, and that's just 1. So that's what I'm talking about when I say we're going to simplify a sequence of elements. And so here we have an example of that. Okay, let's, I wonder if I could somehow have this screen on the side. I'm not really sure, but let me do a screenshot of this guy. Like that. And maybe there's a way to bring it back at some point, because I'm going to have to erase this now. And we're going to do some problems. We're going to simplify sequences of elements. So here's an example. Simplify fr squared to one of the 6 elements of D3. fr squared to one of the 6 elements of D3. Oh my gosh. So this is a brand new kind of math that you've never seen before. But believe me, we can do it. In fact, I'm going to show you 3 different ways to do it. And you can learn them all. You can learn just one, or you can learn maybe 2 of them and just apply whichever method seems appropriate. But I'm going to show you 3 different methods. Okay? And the first method uses my triangle. The first method uses this triangle right here. And what I'm going to do, and I'm going to draw the triangle diagrams here so we're not relying on this piece of paper that I have. So in fact, I'll just do that. Three different solution methods. One, use the triangle. And I'm going to do that right now. So I'm going to start with the original position, right? A, B, C. Now, if I flip it, I mean, all these intermediate steps are going to look the same from afar, but the vertices are going to be in different places. Anytime you flip across the vertical axis, the top stays the same, and the corners flip, the bottom corners. Okay, then I'm going to rotate. So I have 1, 2, 3, 4 things that I'm going to do to it. I'm going to flip it first, which I just did. Then I'm going to rotate it. Then I'm going to flip it again. And then I'm going to rotate it twice. Ooh, brand new math, brand new math. But this is like arithmetic. It's just with symmetries, with these different isometries, with rotations and flips. Remember, those are the building blocks, some of the main building blocks of symmetry. So rotating this now, C would go down here, bottom left, B would go bottom right, and A would go on top. Okay, so the third thing to do is to apply another flip to it. And I would leave the top alone, so A on the top. B and C. And then I'm going to rotate it 2 more times. You could break it into 2 steps, but I think I'm going to just do it all at once. So A would go from the top first to bottom left and then to bottom right. So that's going to be A. I'm doing all the rotations counterclockwise. So B would go from bottom left, bottom right, and then top. And C would be here. Okay, so I'm done doing all these different maneuvers. Now the question is, where did I end up? I know how I got there. I did these 4 different maneuvers, F, R squared. But where am I now? Which one of the 6 am I looking at? So this is when you bring that and you can have this in your notes when you're doing the test. I have to talk about, by the way. Set arithmetic. I'm going to bring up that file. So let's see, B on top. So B on top, and then C and A. So I'm going to just share this with you. Again, you can have something like this in your notes. So it's B on top, and then C and A. That looks an awful lot like the R, right? It was B on top, and then C and A. One way to read it would be, because we started with A. Our original is A, B, C, with starting from the bottom left. So you could always start with that. So that one way to call this R triangle would be CAB. So that would be, that's one way to look at it. Oh man. So yeah. Oh, so I lost that. So it was C, A, and B, and that's R. So what I just found out is that F, R, F, R squared. When you simplify it, it turns out to be R. This is the kind of problem that you're going to have this on the test. Okay, it's going to be one problem out of several, but if you want to get 100 on the test, then you're going to want to learn this. You can have notes on the test, and so what I would definitely have is those 6 triangles. You can even have examples. Okay, so F R squared can be simplified to simply R. Now, I promised 3 different ways to a solution. So let me show you the other 2. So second way is using the multiplication table. What? There's a multiplication table? Why don't you tell us right away? Wait a minute. You can just multiply these with the multiplication table? Well, yes, you can. At the bottom of the page 141, there's a multiplication table. I don't know if you can see that. Some light on it. So I'm magnifying this multiplication table here, page 141. Of course, everybody has the book by now, right? Yeah, so I'm giving you 3 different ways to do it. I would also encourage to, if you like using the multiplication table, then you could have that in your notes. Okay, so I'm going to use the multiplication table now to solve the problem. So I have F, R, F, R squared. So the multiplication table works, it's a 6 by 6 table. It's like multiplying numbers. You know how you had, back in the day, you had, this, what did they call them? Times tables, right? This is like a times table. I mean, that's exactly what it is. So if you want to find out like 3 times 4, let's say, then you go to the 3 row, and then you go to the 4 column, and you see that that's 12. So 3 times 4, or alternately, you could have said, well, I could just do 4 times 3, right? And then you can find that it's 12. The issue here is that if you do, let's say, R times F, it turns out that it's not the same as FR. And that's what makes things complicated. You can't actually just kind of move things around. Like you might say here, well, you have F here and R here and F. Why don't you move the R and the F, reverse the R and the F in the middle, so you'll have the 2 F's together and then the R's together. That would be super easy, but no can do. Can't do it. it's because r times f is not actually fr squared. In fact, you could see here, if you have the multiplication table, r times f, r times wait, what did I just write here? Wait a minute. I think I was thinking sorry. What I meant to say is f times r is not rf. I mean, what I was trying to write is r times f is not fr, but I put a square in there because I was thinking ahead a little bit. Fr actually turns out to be r squared f. That's what my mind was going there already. Anyway, when you look at the multiplication table, you can see these little tidbits that if you combine f and r, it turns out that it doesn't work like the numbers 3 and 4, or any two numbers, where 3 and 4 is the same as 4 and 3. F and r is not the same as r and f. F and r together is actually r squared f rather than rf. So that's what makes things complicated. So what we're going to do now, using a multiplication table, actually there's lots of different options, but you could say, what if I just do f times rf? I'm going to do f times rf. And so from the multiplication table, f times rf is one of the elements, right? F times rf turns out to be r squared. F times rf is r squared. And then I have another r squared right there. And now r squared times r squared is r to the fourth. 2 plus 2. And that is just r. Now, why is it just r? Well, remember, r cubed, r to the third, was 1. So anytime you go around a full rotation, it just starts over. So if here's r, I mean, here's the original, r squared, r cubed, and I'm back to the original. R to the fourth is just the same as r. It's just I might feel a little bit dizzier. Notice that it's the same answer, of course. So let me write a little bit of something about the rotations. Like if you have, let's say, r, that's the same as r to the fourth. That's the same as, and I'm going to just keep adding 3 each time. That's the same as r to the 7th. That's the same as r to the 10th. So these are all equivalent. Okay, it just keeps going. You can add 3 to the exponent, and it doesn't change anything. It all boils down to just one rotation past the original. You could even go the other way. What's r to the first? I could write 1 here. What's r to the first? And I rotate the other way once. Basically 1 minus 3. I could do 1 r to the minus 2. Now that's just weird, right? So this minus, by the way, just means rotating the other way. Is that Is that a lot to take? So you can add or subtract 3 to any exponent and nothing changes. So r to the 1 is the same as r to the 4th, r to the 7th, r to the 10th. I mean, heck, I could even say r to the, let's see, 100. I would feel really dizzy because I would have gone, I'm trying to write 99 in here. I'm trying to, just writing with my keypad is just difficult. But anyway, r to the 100 is really just 33 full rotations. That's r to the 99. And then 1 over. So I can add any multiple of 3's to the exponent and nothing changes. Same thing with, if you have r squared. That's the same as r to the 5th. That's the same as, these are both equivalent to r to the 8th, and so on. It's a little weird, but it does work that way. Now, if I went the other way, you could say r to the negative 1. Now, what do I mean by going the other way? Let me show you. R squared, if I start in the original with A in the lower left, B in the lower right, C at the top. If I do r squared, that means rotating twice counterclockwise. So A would be on the top, and then B on the left, C on the bottom right. Now, that is the same exact thing had I started in the original position and then rotated once clockwise. That's what that means. But if you ever see a negative exponent, then you can just add 3's to it to make it positive. Like, let's say I saw this in a problem, let's say -7. It's like, oh, I don't like that at all. I'm going to go ahead and add a 3 to it to make it positive. Wait, that's not enough. How about 2 3's? That's 6. Ah, not quite enough. How about 3 3's? I'm going to add 9. Now that works. I'm going to make it positive. I can add any multiple of 3 to make it positive. So r to the -7 is the same as r squared. That's good to know. That's the kind of simplification you can do when you know that you can add any multiple of 3 to the exponent and nothing changes. Okay, so what's my third strategy?
Professor, before you move, can I just ask a question?
Of course.
How did you get the r cubed or r squared on the beginning of the equation by multiplying f times rf?
Right, so that's from the multiplication table. So I go to the f column, and I'm sorry, f row. So that would be the 4th row. And then I move to the column that's called rf. So I move over to the 2nd last column, and it's giving me r squared as the product of f and rf. So I'm using the multiplication table, the times table, if you will, to get the rf. If you don't have the times table, then the multiplication table is on page 141. I could take a picture of that, but you know what? You really should have some type of access to the book at this point. So the third way is use the fact that FR equals R squared F. Now this is, the other two methods are kind of explained in the book, but this is my own method that I found extremely helpful when I'm doing this. A lot of times you don't really need the multiplication table, and you don't have to go through the whole rigmarole, the twists and turns of the triangle. Really, so many times, all you have to do is use this one identity, and that's the fact that FR is R squared F. Now let me show you how that works. So I'm going to take the original problem, FR F R squared. This will be the third method, right? By the way, I have a video on YouTube where I explain the three different methods using a different problem. So I already put that on the Blackboard content. On the week 6 Thursday, you'll find a YouTube video. You should watch that. If this is not clicking just yet, then watch that video. Okay, so here you see how the whole thing begins with FR. So I'm going to substitute R squared F for that. So instead of writing FR, I'm going to write R squared F. And then what do I have left? I have F and R squared. Now, remember, F and F, if you put F and F together, what do you get?
1.
That's right. So you get F squared, which is equal to 1. And so I'm going to cancel that right out of there. So what I have then is R to the 4th, 2 plus 2. I'll write it like that, R to the 2 plus 2. Sorry for the mess. Which is R to the 4th, which again, of course, is just R. Because you can add or subtract any multiple of 3 you want, whatever makes it easier to work. So with each of these three methods, I got R as the solution. They can all be used. Sometimes one of them is going to be a lot easier than the others. I like this third method because, honestly, you only have to remember one thing, and you don't have to have with you any notes or anything like that. All you need is this one identity, and if you apply it in a clever way, you can use this in all of these problems. All right, so again, I know it's a lot to take in, and this is a lot more mathematical, or a lot more calculational than some of the lessons that we've had up to this point. And I'm going to say right now that this is one of the hardest things. I would say in the top 2 hardest things that you'll see in this class from a mathematical standpoint. I think the main thing is it's just new. It's not like the math is hard. It's just you've never dealt with these rotations and flips before and how to combine them. And so here we are, learning something new. Go figure. Hey, it is college after all. So you will practice it. You will study the book. I'm going to give you a homework assignment right now. And the homework will be read section 5.2. You're going to work problems for, let's say, for, where did I decide already? I had this on Blackboard. Hold on. 4, 5, 7, 8. Let's put that on there. 4, 5, 7, 8. And then, on top of all that good stuff, I have a project for you. And that's already on Blackboard as well. Let's see if I can copy it here. I bet I can't. Yeah. Okay, so what I was trying to copy is create 2 original point symmetry patterns, one with less than 4-fold symmetry and one with more than 4-fold symmetry. Let's see if I can, oh, here we go. Okay, this is silly. Create 2 original point symmetry patterns, one with less than 4-fold symmetry and the other with 4-fold or more. So for instance, you could have a C2 and a D5, or a D3 and a C8, or something like that. By the way, I could talk about these different groups quite a bit more, and I will next time. For instance, C3 is almost the same as D3, except it doesn't have the flip elements. So, you know, if you allow me, I'm going to spend just a couple more minutes here talking about the different Rosette groups. If you have a C1, then all you have is one position. That's it. Right? Remember C1? No flips, no rotations. Then all you have is that original position, right? So the only element in that type of symmetry group is the original, what we call identity. For D1, you have that, and then you have one flip. Like, remember the True Religion logo, or the, what was another D1 that we looked at? We saw, like the McDonald's arches or something like that. You can flip them and it looks the same, but there's no rotation. So there's 2 ways you can orient them. This way, the arches, you know, the golden arches, the McDonald's one, or you could look at it from behind and it looks the same. So you got the original and you got a flip. Makes me think of flipping burgers, but that's kind of not the point. You're flipping the logo. You're not flipping burgers. Flipping the logo is a lot better than flipping burgers. Veggie burgers, maybe. C2, can anybody guess what kind of elements we would have in C2? And this is getting a little abstract because you're not actually looking at actual examples. You're kind of thinking, what could we have in C2? We don't have the flip elements. Basically what you have, like in the letter S, you have 2 rotational positions. This one and this one. Do they look the same? You bet they do. Because if that first one's original, if this is original and this is rotated upside down, but I can't tell the difference. But that's what it means to have two rotational positions, right? If this was A and this was B, I'll put those in here. If this was the A end and this was the B end of it, then once rotated, which would be the R element, would have it like this. And that's all there is to it. It only has the original and then once rotated. That's C2. So what would D2 look like? And my point here is showing you that once we understand the D3 symmetries, the symmetries of the equilateral triangle, then looking at the other symmetry categories is not that much more complicated. In fact, a lot of them are easier than D3. All of these are actually easier because they have less of those elements. D3 had 6 elements. D2 is going to have the rotational elements of C2 plus then the flip elements. So in fact, the D groups always have twice the number of elements as opposed to the corresponding C group. So D2 has 4 elements, 1, R, F, and RF. The 1 and the R are the rotational elements. There's no F in there. And then F and RF are the F elements. Basically, I'm just slapping on an F to the first 2 elements. That's 1 times F and R times F. C3 is just 3 rotational elements. I have 1. Every list always starts with 1 because that's the original. So 1, R, and R squared. So C3 has 3 elements. Wait, I think I might see a pattern here. Let's just look at the C groups here for a sec. So C1 has 1 element. C2 has 2 elements. C3 has 3 elements. Can you guess how many elements C4 would have? Who's with me? That's right. That's right. So C n has n elements. If I lost you, that's okay too. Don't worry about it. You can watch it again or not. That's okay. This is kind of to put things into perspective. With the other groups. D3 is really the one that you need to focus on when it comes to the test and when it comes to the homework, the problems from the book. But you should know that all these other groups exist as well. So what about D groups? If Cn has n elements, like C4 has 4 elements, C5 has 5 elements, C10 has 10 elements. If I have a D, let's say D10, how many elements do you think I would have there?
10.
D10 would have 20 elements.
Oh yeah, duh.
Yeah, C10 has 10 elements, D10 has 20 elements.
Okay.
So because you have the rotations, the 10 rotations,
Yeah.
and then you have the flip elements. Okay, so this is getting this is like the limit of how far we're going to go, and it is 6:25, which means it is time to stop. But this is what the other groups look like, and there's always examples, nice examples for these things. Like D2, you could look at a rectangle. D3, we looked at equilateral triangle. D4, you could look at a square. The regular polygons actually make the easiest and the clearest examples of the D elements. Alrighty, so read section 5.2, work those 4 problems if you can. We can look at them, we will look at them next week, Tuesday, and then the project. And we will have a test coming up, but we'll talk more about that on Tuesday. I'm thinking it's probably during week 8, either Tuesday or Thursday, whichever day you guys want. Probably Thursday. You know what? Let's just go ahead and make the announcement. What would that be? That would be March 18th. So let's tentatively have the test in 2 weeks. That gives us some time to review. Okay, so that's that, March 18th. I'm just going to write it here. Let's talk about it more. We're going to talk about it a lot, actually, next Tuesday, like what you can have and how we're going to actually do it. So the midterm will take place March 18th. Let that be
Professor?
known. Yes.
Is there going to be like a study guide or something that we could look at to prepare for the test?
Yes, you bet. I already have them ready. And but let's worry about this for now. Yeah, there'll be study guides. You could bring notes. You can have a calculator. Oh my God, this doesn't sound like the kind of math test I used to take. Anyway, let's stop here. Email me if you have any questions. Blackboard has some YouTube videos and things, and then of course this is recorded so you can watch it again. Hopefully it'll feel a little bit less intimidating the second time. Okay, have a great weekend, everybody.
Thank you, Professor.
Thank
Thank
you.
you. Have a good one.
Bye. Bye. Sleep well. Don't worry about this so much. Think about it tomorrow.